about handing in the homework. How can we get credit on Autolab or no? Hard the dog's fine. We won't get a doggo visit today though. You submit to the homework on Autolab. I think I might know what you're asking here. Let me pull it up. No, I'm not signed in on Autolab though. So when you go to Autolab, I am signed in. You won't submit anything to the application objectives or learning objectives ever in this class. These are just for me to be able to say whether you've completed an objective or not. These are strictly for feedback to you. You can't submit to any of these. So if you're trying to submit to this, there's no way to submit. If that's what you're asking, go to loading. You go to the other section where you can submit the homework. So go to Objective 1, Program Execution. These objective categories, these are where you're making your submissions. So you go to application, either Physics Engine or Rhyming Dictionary. This is where you submit the appropriate homework. Then you'll get feedback. You can see your feedback on how you did on all the lab objectives and how you're doing on all the objectives. And I left the lab grader in there just so you can still get that feedback. If you didn't finish the lab, I highly recommend still finishing that because it'll make completing the homework assignment itself much easier. The lab is designed to start you off, give you a good start with the homework itself by forcing you to do some test-driven development. Write the tests first and then start doing some development. And you also have to add some tests beyond. I hope I got a 2.0 beyond what you have. And eventually you can get all smiles like this. This is what a perfect full credit submission looks like. Should I open my code? So there's no Google form anymore. The lab, just click on this. I'm not logged in here, but you log in with your UBIT, and it'll take you right to the form after that. The link that it gives you after you click the start, whatever it was. So don't click the link on Piazza. Find the link in the course website and click that one. All right, let's talk about some polymorphism. Google Drive, I do not care. Do not care about the change you're making to the trash bin. If I throw something in the trash, I expect it to be deleted. And I go to Google Drive through so many different platforms. I have to click that on every friggin' one of them. So let's talk about polymorphism. Last time we introduced inheritance. Now we're talking about polymorphism, which I see as one of the huge payoffs for using inheritance. This is where we're going to see where inheritance actually gets a lot of the power. I know I motivated it with some things last time. We factored out common functionality. We had that functionality shared between multiple classes by extending it. But you might not be convinced that that's, the best thing, the greatest thing in the world. Polymorphism should get us the rest of the way there so we can talk about why else to do this? Why else should we organize our code like this? Because so far all we did was add more work, add more coding, add more files, and add more complexity to our projects. Why would we want to add all that besides the benefits that we talked about last time? To that end, we're going to extend the lecture question from Monday, and we're going to use a little bit of polymorphism. We're going to, with our flashlight, boombox, and electronic functionality and battery, we're going to add to that an object named useElectronics that has two methods that are, you guessed it, using these things in different ways. UseAll, which takes a list of electronics and calls the use method on every single one of them. And a method named swapBatteries, which takes any two electronics and, as the name implies, swaps their batteries. So the one electronic should have, after the method call, have the battery from the other one, and that other one should have the battery from that one after the method is called. So similar to replace batteries, but it's between two electronics, swapping their batteries. And testing is making a return, a test electronics test suite that tests all of this functionality, at least the use electronic functionality, since the rest of the functionality was already tested. If you have Monday's lecture question done, you already tested that against my test cases, and using your test cases from last Friday, you already tested that stuff. So this does require, occasionally I'll have lecture questions like kind of this is a 3-parter here. This does require having the functionality from Monday's lecture question. So if you haven't finished Monday's lecture question yet, you can think about this one, how you're going to do use electronics, but you can't, don't bother submitting for this one yet. Make sure you have all the functionality and full credit for Monday's lecture question, because you need that code as a starting place for this one. Usually these things can cause cascading failure. Well, I didn't get Mondays, how am I going to get this? But since the deadlines don't really mean anything in this class, I feel like I can get away with that. You still have to do Mondays anyway, so I don't think we have that issue. But feel free to complain to me about it if you want. It's your right to do that. How can we make bots with projects and reCAPTCHAs passing? Just work hard, I guess. All right, so let's talk about this. We talked about inheritance last time, and we ended with this diagram of the inheritance hierarchy in Scala, or the type hierarchy, as the slide says. But this is all the inheritance. Every arrow means that this type inherits or extends this type, and we can follow the arrows for this whole diagram. So we have two major types of types, I guess. Two different major types of types. We have all these types, which I commonly refer to as primitive types, because they'll compile down to primitive types on the JVM. These are any types that extend any val. So, and this is a comprehensive list of them all: double, float, long, int, short, byte, unit, which doesn't make too much sense. Boolean and char. They all this doesn't make too much sense in terms of stack and heap, which I want to talk about. But all of these extend any val, which extends any. So all of these types are going to be stored on the stack when you create variables of these types, except with the exception, I didn't make this clear enough last semester, so I want to emphasize this more, unless they are part of an object. If they're a state variable of an object, then they're going to, and that object is on the heap, then they're going to be on the heap along with the state variables of that object. But if you're working on the stack, in the stack frame, not creating a new object on the heap or messing with a method call, then your values and variables of these types are going to go on the stack. The next available slot in memory on the stack, that's where that memory is going to be allocated. Everything else, which is everything that extends any ref, everything else, including every single type that you write, is going to extend any ref, which also extends any, and anything that extends any ref is going to go on the heap. So this is a kind of a quick cheat sheet. What goes on the stack, what goes on the heap. All these go on the stack. Everything else goes on the heap. List and option, these are just two, they were trying to keep the size of this chart down quite a bit. But any other types are going to go on the heap because they're extending any ref. And you can kind of get the idea from any ref, any val. Any val, they're just values, and they're passed by value. They're copied by value when you call methods with these. Any ref, these are storing references to objects that are on the heap. So they're always going to be passed by reference when we use these, when we give them as arguments to methods, give them in constructor calls, etc. It's always going to be passed by reference. And when we reassign values, when we assign values to each other, passed by reference always. So hopefully that much is clear. We're going to start talking about some implications and use some polymorphism here and define polymorphism. Yeah, any val is, I'll refer to them as the primitives. There's no primitives in Scala. These are all technically classes, and we create objects of their types in Scala. But once it's compiled down to Java bytecode, these all get mapped to Java primitives. So they still behave as though they're on the stack, because they will eventually, when our code is compiled into Java bytecode and then actually ran on the JVM, these values are going to be primitives and they are going to go on the stack. Even though that's not how we code them as though they're classes and objects. Thanks, Mechatronic. We code them as though they're classes and objects. And they have methods and all that goodness. But when they are compiled, they're going to be primitives and they're going to be on the stack. Yeah, get me out of here. I got a few announcements. I forgot about announcements today. Do I have Piazza? Oh, I can't really go to... Can I go to Piazza? Let me do it on a different screen first. Sorry about this. Just give me 1 second. I got a few announcements that I forgot about. Yeah, I think I'm safe here. I gotta be careful with Piazza because even when you post anonymously, I can see your names. So I want to make sure I don't dox anyone. But we do have a review session tonight, right? Yesterday? That should say 9:23, right? After lecture today at 4 p.m., there's going to be a review session. A few of our TAs, tonight. So that's supposed to be 9:23. Tonight at 4, they're going to stream on Twitch, similar to lectures. Check out their Twitch channel when they go live, and I don't know, get some more learning, get some more education. I don't know what more to say. It's a review session. They're going over, there we go. They're going over inheritance. So mostly Monday's lecture tonight. So, or not tonight, but this afternoon. So check them out. They're going to try to make this magic like that got fixed. I believe they're planning to make this a weekly thing. Every Wednesday. We've talked about this for a while, but I just want to make sure I don't say something that isn't actually completely accurate. But anyway, every Wednesday, 4 to 6, check them out. Since they are streaming, you can always watch the VODs on Twitch. If you can't make that 4 to 6 Eastern time, watch their VODs on Twitch so you can still get that information out there. This class goes fast. In lecture, I have to cover a lot of ground really quick, so this is a good way to get that material reinforced, get an extra 2 hours of explanations each day, interact with them, ask them questions, all that good stuff. Take advantage of this. It's something that there seems to be a lot of demand for. Since lectures go so fast, they can take their time, they can slow down, they can go very slowly through examples. Please take advantage of that, especially if you're overwhelmed in this class, which seems like most of the class is overwhelmed right now. Please take advantage of this and check them out. The other announcement, UB Hacking. Check them out as well. The post is pinned, so you can get this information on Piazza. Make sure you check it out and get more information. I can just go through it quickly now. But October 24th through 25th, UB Hacking. Please at least consider going to this. I highly recommend it, even though a lot of students, when they're freshmen, when they're in 116, 115, they always think, oh, I can't go to the UB Hacking because I don't have the skills. I can't really build an app or anything. It's nonsense. You have a lot of skill. You have a lot of capability now, especially by the time we get to the end of October. You're going to be able to do a lot of really cool stuff. And even in 115 students can get a lot done at a hackathon. And even if you don't, just go there, virtual, but go there virtually, soak up the environment, the atmosphere, and just get some inspiration. Even if you don't end up building a project, just go check it out. Go see what it's all about. So I highly recommend it. I usually it's in Davis Hall, and we take up all of Davis with food, and everybody's just all over the building, taking up all of the common space. I just love the atmosphere. I go there every year to just soak it up. Kind of sad it has to be virtual this semester, but I think they'll still be able to capture that atmosphere and that excitement. And unfortunately, no food this time. As maybe they'll mail you a slice of pizza if you register early. But registration is open. You do have to register for the event, so check out ubhacking.com. Get registered. Check it out. All right, and with that, let's get back to some polymorphism. And you're seriously, with what you do and with what we do with you guys, with y'all in 115, 116 these days, you can build some really cool stuff now. Just with your 115 knowledge, you can build a full stack web application. That's not nothing. That's huge. That you can take an idea and just build something really phenomenal with that. And with what you're learning now, I mean, it's just more stuff that you can do. You can come up with an idea and build it pretty well with what you know now. So anyway, back to polymorphism. So stack, everything that extends any val, which will only be these classes, are going to go on the stack. Everything else on the heap. So quick review. I know I showed this slide quite a few times, but quick review for your lab tomorrow and for your interviews this week when you're asked about stack and heap. This is kind of your cheat sheet for that. Stack and heap. And then look through all the lectures from last week to get all the details of what that means. What stack and heap mean. If you're still asking that, review last week's lectures. All right. So let's talk about what we did. What we did last time. We talked about this game that we were building. We're going to continue with this example and talk about more implications that we can do now that we have this inheritance structure. We have these two objects that can be manipulated by players in the game. They both extend inanimate object, which is where we factored out all their common functionality and added them to this abstract class, inanimate object. We defined the methods that this class has and also the variables that it has. What this does when we use this inheritance structure is we guarantee that every object of type ball or health potion is going to have a location, dimension, and velocity, and will have methods object mass, use that takes a player, reference, and magnitude of momentum. Each one of these will have all of that functionality, and we can guarantee that because we extended the functionality of inanimate object. Now, each of these objects of these types have different implementations for object mass and use of player. Different implementations, they do different things, but we do know that they have those implementations, which is going to be important when we start talking about polymorphism in like the next slide. Inanimate object also extends dynamic object, so we can guarantee that every inanimate object, which includes these two types down here and any extra types that extend inanimate object, we know that they'll all have location, dimensions, and velocity because they are dynamic objects. And we call this an is-a relationship. A health potion is an inanimate object, which is a dynamic object. And by transitivity, health potion is a dynamic object. So it gets all of the content of all of these three types. So our classes all go right here in that inheritance structure, all this type hierarchy. And our class now has 6 different types. If you follow all that, you have to look at the code for Physics Engine a little bit as well. But our class that we created, health potion in this example, if we create a new health potion, we can store it in a variable of any of those types. And any type in its type hierarchy. So our class, health potion, which extends inanimate object, so it is an inanimate object, which extends dynamic object, so inanimate object is a dynamic object, which is a game object, which is where you'd have to look at the Physics Engine code a little bit, since I didn't put that in the slides. But dynamic object extends game object. Game object doesn't explicitly extend anything. So anytime we have a class that we write that doesn't explicitly extend anything, it implicitly extends any ref. You can make this explicit. We typically don't, but you could do, in the game object class, you could say extends any ref, and it's going to have the same behavior, just making that explicit instead of implicit. And then any ref, of course, extends any. So health potion, when we create a new health potion, it is an inanimate object, it is a dynamic object, it is a game object, it is an any ref, it is an any. So we can store objects or references to objects of type health potion in variables of any of those 6 types. So all of this compiles, everything works, and we can use these variables, all these variables of these types, to store health potions. There's one thing that we lose with this. So polymorphism, the name comes from poly meaning many, morph meaning forms. So polymorphism means many forms. A health potion has 6 different forms that it can take, and it can kind of morph into any one of those. It can behave as any one of these. So whereas normally we can't have a variable of a specific type storing a reference to an object of another different type, we usually can't do that, but we can if they extend each other. A health potion extends game object, so a variable of type game object can store a health potion because a health potion is a game object. So this is where we get the name polymorphism from. This health potion type can take on 6 different forms. So it's polymorphism because we can store a value in a variable of different types as long as it's higher up on the inheritance tree. that it eventually extends that. So what we lose from this is we can only access the state and behavior of the variable type, or values in this case, of the type of the value or the variable that's storing that object. So once we store a health potion in an AnyRef, we lose all access to the health potion specific code. So, for example, magnitude of momentum is defined in the inanimate object class, like we did on Monday. We added that method to the inanimate object class. So if I have a health potion, a variable of type health potion storing this health potion, I inherited, health potion inherited that method from inanimate object. So potion 1, this variable of type health potion, has the method magnitude of momentum, and you can call it and everything's fine. Potion 2, inanimate object, well, inanimate object is the type that defined the magnitude of momentum code. So when we call potion 2.magnitude of momentum, we still have that method. It exists in the inanimate object class, so we are able to access that functionality. But when we get to dynamic object, the dynamic object class doesn't know anything about the magnitude of momentum method because it was defined in inanimate object. Inanimate object extends dynamic object, but dynamic object doesn't know anything about an inanimate object. So when I have a variable of type dynamic object, I cannot access that method because dynamic object, the class, doesn't know anything about the magnitude of momentum method. So even though this is potion 3 is storing a health potion, which does have a magnitude of momentum method, since we stored it in a variable of type dynamic object, which is a legal assignment, health potion is a dynamic object, so we can do that. But since we're accessing the health potion through a variable of type dynamic object, we do not have access to methods that are not known to the dynamic object class. And parents don't know about their children. Good way of putting it. So dynamic object, same with game object, AnyRef, any. None of these types know anything about the magnitude of momentum method. They didn't inherit it from anything. They didn't extend a class that knew about this to be able to inherit it. They don't know about this method, so variables of those types can't access this method even when they're storing an object, a reference to an object that does have that method. We cannot call it because we're storing it in a variable of a type that doesn't know about that method. So why would we ever do this? Is a big question. So that's like so that's what polymorphism is, by the way. Polymorphism is storing a value in a variable of different types. So here we're not taking advantage of polymorphism because we're storing a health potion in a health potion variable. As soon as we store a type, an object of a type in a variable of a different type up its hierarchy tree, that's what polymorphism is. If you have an interview in a few weeks when you're interviewing for Learning Objective 2 verification and your TA says, "What's polymorphism?" That's your answer. It's storing types, objects of one type in a variable of another type up its hierarchy tree. That is what polymorphism is, and what happens when we do this is we lose some functionality. Like, that's polymorphism. That's it. The rest of this week and next week, all we're talking about is implications of this fact, implications of polymorphism, and to an extent inheritance, but inheritance is really just something that we use to be able to use polymorphism. Where inheritance is actually extending. Health potion extends an inanimate object. That's inheritance. This, storing these objects in variables of different types, that's polymorphism. That's the crux of these 2 weeks. These 2 weeks of OOP. If you got that down right now, you're going to be in good shape for the next 2 weeks. If you don't, hey, you got another week and a half to really let that soak in. So why would we ever want to do this? If all polymorphism does is restrict our functionality, why would we do that? Why not just always store health potions in objects of type health potion? It would give us all the functionality of a health potion. Like, for example, a health potion has a volume, inanimate object doesn't. So once I store a health potion in an inanimate object variable, I can't access its volume through this variable anymore. The functionality still exists, so if I can get this in a health potion variable, I could use it again. But I can't access its volume anymore, this volume of 6 from the constructor, if you remember all the details from last lecture. So why would I do this if it just restricts functionality? That's silly. Why would we do this? So the reason for this is to simplify other code. So this is going to make working, if I store a health potion in a variable of a type that's not health potion, I'm just losing functionality. It makes it harder to work with that health potion, but it can make other code simpler. So recall our player class. We had a class named player, and a player can either use a ball or a health potion, which takes ball and health potion respectively. And we had these two methods. But what happens when we want to add more object types to our game, more inanimate object types? Well, each time we do, we're going to have to go into our player class and modify this class. We're going to have to add a new method for that particular type. If we want 20 different types of inanimate objects in our game that the player can interact with, and maybe we want the player to be able to store an inventory of all these different items, and maybe we expand the game like that, we're going to make a lot of changes to this player class. At a very minimum, we're going to have 20 methods, one for each of those types. This is where polymorphism comes in handy. This is where we really get to see the power of it. So I'm going to combine these methods into one method called useItem, or useItem instead of useBall or useHealth potion. We're going to call it useItem, and instead of having it take a ball or a health potion, I'm going to have it take an inanimate object as its parameter. Now I only need one method. I can only treat the parameters as inanimate objects. I can't get ball or health potion specific functionality out of this thing, out of this item, but I can take any inanimate object. So any class that extends inanimate object can use this method. This method can be called with any one of those things. So use item of some health potion, cool. Use item of of a ball, cool. This one method, does everything that we need for any inanimate object. And now when we add those 20 objects, guess what we don't have to do is edit the player class anymore. So we write the player class once, and it can handle any inanimate object that we ever can dream of later in the future. It can use any of them. So now when we use our players can use balls, they use health potions, they can be stored in variables of ball and health potions, so we still have the ball and health potion specific functionality available to us out here, but then when we give them to the player only cares that it's an inanimate object, and then it can use them as those inanimate objects. So when we call player1.useItem of ball, we have this implicit assignment. We create a variable named item of type inanimate object and assign it equal to the reference of the parameter of the argument. So here we have this line that we can imagine val item of type inanimate object equals ball, which is this new ball with zeros for all its physics vectors, just for the sake of slides. Yeah, it has 0 for dimensions. It doesn't make sense, but and then 5 mass. So we have an item. It happens to be storing a ball, but we're storing in a variable of type inanimate object. So we can only access inanimate object specific functionality, but we're able to have just one method to handle any inanimate object of any type that extends inanimate object. And recall that inanimate object has a use method that takes a player as its parameter. So since we can guarantee through the inanimate object class that everything that extends inanimate object has a use method that takes a player, we can call that use method through this variable of type inanimate object. We don't know what the use method is going to do, but we know it has to exist. Whenever we extended this class, we had a contract to fulfill. We have to implement the use method, or else our object would have to, or our class would have to be abstract. So once we know that everything that extends this thing has to implement a use method, we can take advantage of that and say, well, I have some inanimate object. I don't know what it is, but I know it has to have a use method that takes a player and returns unit. It has to, because that was part of the contract of the abstract class, that anything that extends it eventually has to implement this use method that takes a player and returns unit. And then it's up to the extending classes to decide what that method should do. In the case of a ball, the player throws the ball. In the case of a health potion, the player drinks that health potion. Two very different behaviors. So, and we don't care what the behavior is, but we do care that that behavior exists, that there is something that's going to happen when we call this use method. And when we write the player class, since we're never changing this again unless we're fundamentally changing the game, guess what we're doing is only testing player once. This is something very important that we want in our programs. In this course, most of your stuff, most of the assignments will be designed to help you with this. But later on in your career, this is something very important to design for, is design for easy testing. With this design, I can test player once, and then as I expand my game for the player to be able to use and interact with all kinds of different objects, I don't have to retest the player class. As long as I test once and make sure that I have some test cases where the use item method is called with any inanimate objects, and making sure that the use method is called, I'm testing player once and then calling it good. You'll see this in Physics Engine, and if I get to it, if I have enough time, I'll talk about the Physics Engine a bit. In the Physics Engine, for example, in dynamic object and static object and game object, you have these methods in there that don't do anything, and all they do is update some bookkeeping variables. And if you're working on that assignment, if you did the pre-lab for that assignment, or the pre-homework lab for that assignment, you realize that it's really silly that these methods are just being called to be able to check some variables, some bookkeeping variables were updated just in the testing. But as long as we test that functionality and know that it's fine, we can start using that code that's tested and works with any type of dynamic object and know that it's going to work because we already tested it, even without knowing what actual types of dynamic objects your code is going to be used for. So you're building this game, this jumper game, you're building the physics engine for it, but when you're building the physics engine, you don't even have to care about any of the details of the jumper code. You don't even have to look at that code at all, even though that code is being used extensively, is using your physics engine extensively. You can test your physics engine without actually knowing the application. This is something that we call encapsulation. That physics engine is encapsulated in its own environment. We're able to test it independently of any of its applications. So we can take this one step further with our extensions, and I updated the variable names here. You can name these the same; it works fine, but it does get you in trouble in certain situations that I want to avoid. But we can change the player class to also be a dynamic object. So let's change this class that we saw on the previous slide and on Monday. You can change abstract classes. An abstract class can extend another abstract class. We have the player, and we can have this also extend dynamic objects. So let's rewrite this to take all of the same constructor variables. We don't want to change our constructor, but pass those two values from the dynamic objects constructor to it. So location and dimensions, give those to the dynamic object class constructor. And then also assign the velocity. This is where we need different names. This is a situation where you have to have different names in your constructors. This dot velocity is referring to the velocity state variable that's inherited from the dynamic object class. So we don't want that to be confused with the velocity from the constructor of the player class. So we can get around this by giving them different names. Here I just threw an underscore in front of them just to give them different names with basically the same name to us humans, but different names to the computer. In an underscore, variable name that starts with an underscore usually means this is a private variable or variable that is only used internally to the class. which is the case here. Nobody else has to care about these variables except just passing them along to the dynamic object. So the dynamic object velocity variable, we're going to assign that the value of this velocity variable from the constructor. And the rest of the method, the rest of the class is the same. You don't have to use override unless the superclass is the same method. If you use override when you are not overriding something from a superclass, you're going to get an error. So now, this is a lot of code, but it's mostly cut and paste. It's creating a bunch of objects. So don't get shocked at me throwing a bunch of code at you here. So now, what we can do, I have players that extend dynamic object, I have health potions that extend dynamic object, and I have balls that extend dynamic object. So in a very real sense, players, health potions, and balls, any objects of these types, are dynamic objects. So since they're all dynamic objects, they can all be used wherever we could use a dynamic object. So I have all these dynamic objects. I can assign them and use them whenever dynamic objects can be used. So I can also add them in data structures that store dynamic objects. So I have this list of dynamic objects. I can assign this a list with players, potions, and balls all in the same list. This is something we took for granted in Python and JavaScript, where it just lets you mix types like this. Scala, being a strongly typed language, doesn't let you mix types in its data structures. But if you create a data structure using one of the superclass types, dynamic object in this case, we can populate that with anything that extends dynamic object. And even though like health potion doesn't extend dynamic object directly, as long as it's somewhere in its type hierarchy, we can use that as a dynamic object. Health potion extends extends inanimate object, which extends dynamic object. So we can use a health potion as a dynamic object. A health potion is a dynamic object, so we can use it wherever dynamic object can be used. So now we have 3 different types in this list. All those types extend dynamic object, either directly or indirectly. So this is valid code. This compiles, this works, this runs, this is great. So we have this list of dynamic objects with game objects, which has 3 different types in it. We create our game world. If you haven't looked at the physics engine code, the handout code for physics engine, if you're doing rhyming dictionary, and this doesn't make sense, take a quick look at the physics engine, just get an idea of what's going on there, and this will make a lot more sense. This is more for physics engine uses a lot of polymorphism, so I like to use that for examples. So I recommend, even if you're doing rhyming dictionary, at least take a look at that so you can get more examples of inheritance in action and polymorphism in action. So we create a new world with 15 gravity, which I used as a magic number, unfortunately. I should have used 1 extra line. I wanted to fit it on the slide, but I could have squeezed 1 more line in there for gravity equals 15. And then set its dynamic objects, which is a list of dynamic objects, to the game objects. Then I can update the world and have physics just work for all of these types that the physics engine doesn't even know about, but since it's using them as dynamic objects, the physics engine is able to move players around, move potions around the game. It's able to throw balls and nice parabolas and hit other players and detect collisions and all this good stuff. I might get to live coding today. I'm probably going to run out of time, and I don't want to rush these slides. So now all these types work with our physics engine. So if you're working on physics engine, you probably wondered, working with dynamic objects, this doesn't really seem that useful. Well, this is how we use it. We extend dynamic object and then throw all those specific types, these types with game logic built into them, into the physics engine. So we can write our physics engine completely separate from any of our game logic, and we can also use the same physics engine for multiple games. We can reuse all of that code without rewriting a physics engine for every game we want to make. So since it all works like this, we just extend dynamic object and then build whatever we want after that, add whatever functionality we want to it, as long as it has every dynamic object we create, every game object we make, as long as it has a location, velocity, dimensions. We have those 3 things that dynamic object guarantees we have. Those are the three things that you access in your physics engine code, and then everything else works. Why not define each with dynamic object? So I could store these in variables and values of type dynamic object, but this is a way where we can preserve the functionality that we get from the concrete classes. Like maybe I want to access this health potion's volume directly, and I don't want to lose that functionality, which I would lose if I stored this in a dynamic object. So I want to maintain all the game-specific functionality of these objects. But then when I go to give them all to the physics engine so I can get physics working in my game, that's when we take advantage of polymorphism and store them in this list of dynamic objects. I could also do that up here if I realize that I don't need any of the specific code in any of these classes. I can get away with that. I can store these all in dynamic object type variables. But if I don't have to, I want to preserve that functionality. But once we get to this line and I give this to the physics engine cannot access any of the game-specific logic, the volume of potions, the mass of balls, I forget the HP of the player. Things like that can't be accessed or modified in our physics engine because it's only getting these as dynamic objects. Let's talk about... Hey, I got him. Sorry, I heard it as it was coming out of my mouth. Like, that shouldn't... All right, so let's talk about override. We've seen this a little bit, but let's talk about it a little bit more in depth. And talk about references again. So every object that we create extends any ref, which extends any. I mentioned that a few times, but I didn't talk about any of the implications of that. So let's talk about those now. Two methods that I'll be talking about that we extend, that we inherit from any and any ref, are the toString method and the equals method. So toString, this method is called every time we call println. Println will implicitly call toString, and then whatever the string that's returned from toString is, that's what's printed to the screen. The toString method of any ref of the AnyRef class is going to convert that reference to a string, which has its type, an @ symbol, and then the reference, something that represents the reference to the JVM of where it can be found in memory. It's not exactly the reference, but for our purposes, we can think of that as its reference of where it can be found in memory. If you've printed out your own objects to the screen before in your testing, you've seen something like this: the fully qualified name, which is the package and the class name, and then an @ symbol, and then some random characters at the end. This is what you're going to get if you just print out your own types. And then also we have the .equals method, which you've been using in the last few, to test the last few assignments. Back to last Wednesday, is used equal to compare two objects. The default behavior of the equal, it's to call the .equals method. The default behavior of the .equals method of anything that extends any ref is to compare them by reference. And you've been using these in last Wednesday's and Friday's lecture questions to compare two references. So equal with two of your objects of your own type compares by reference. So here I have two health potions with all the identical properties, all the identical state. And when I print these to the screen, I'm going to get the references for them and the types. I have two health potions stored in 3 variables here. Potion 3 is assigned by reference to potion 1. So potion 1 and 3 uses that default toString method, which prints out its reference. These references will be different if you run this code, but the one thing that'll be consistent is potion 1, potion 3 are going to have identical references. They'll be the exact same reference because potion 1 and potion 3 refer to the exact same object on the heap. When I compare these, they're compared by reference. So even though potion 1 and potion 2 are functionally identical, they both have zeros for their physics vector, including dimensions. I don't care if it doesn't make sense. I'm just using it as an example. And for volume, since they're identical, but since they refer to different objects, this comparison is going to be by reference and it's going to be false because these are not referring to the same exact object on the heap. And if you're struggling with last week's lecture questions, let this one digest, let this sink in, that if they're not referring to identical objects, they're not the same. So when I say make sure the references are moving around like you expect them to, you can check that using equal equal and doing this comparison of references. Potion 1 and Potion 3 are referring to the same exact object on the heap. That's the only way we can get equal equal to return true here. Yeah, and it's effectively aliasing. So Potion 3 is an alias for this potion that's stored in Potion 1. So this potion here is aliased. I can access it by either Potion 1 or Potion 3. You can think of Potion 3 as a nickname for Potion 1. It refers to the same exact thing. It's just another name for it. If that helps you understand what's going on. Or an alias. So we can change this default behavior. So if we don't like that default behavior, that's when we use override. Just like we did with health potions, when we overrode the abstract methods, if there is some functionality that already exists, we can also override that. So if we say, I don't want that default toString method, which in most cases we don't because it's pointless information to us. If we don't want that default toString functionality, we can override it and give it new functionality. Instead of toString giving me object type and reference, I want to print out the location, velocity, and volume of this thing. Or whatever else I want to do. You can see an example of this in physics vector. I overrode the toString to print out in parentheses x, y, z, which is how we expect to see physics vectors. I don't want to see physics.physicsVector at some random characters. That doesn't mean anything to me. But if I override that toString and say, give me a physics vector, it's right here. Give me a physics vector of x, y, z in parentheses. Now when I print these things to the screen, I'm going to get it in a more palatable way, something that's more human readable, to be able to represent the values, the current state of that physics vector. We can also override that equals method. So when equal equal, it'll call the equals method if we don't like the default behavior of always comparing by reference and saying, are these two variables, are these two values referring to the same object on the heap, which again isn't really what we want to do. We needed that to test the lecture questions from last week, but for practical purposes, we usually want to override this to check some of the properties. So here I'm going to override this to check if two health potions have the same volume. If they have the same volume, I'm going to consider those equal. We do that using a little extra syntax, a little Scala magic here, the match case statement, which is going to say start with some object, something that I want to refer to, and the dot equals, the method always takes an object of type any. So you can do equal equal and then any type on the other side of the equals sign. So this object, I want to check its type first. I'm going to use a match case statement for that. And I'm going to give a case for each type that it can be compared with. In this case, health potions can only be compared to other health potions. I'm going to store, if it's a type health potion, I'm going to store it in a variable named HP. And then I'm going to use this arrow syntax. Scala, the developers love their arrows, and I'm not complaining. I like them. And this arrow is going to say, if this is a health potion, store it in a variable named HP, and then run this code, which will be some Boolean expression deciding whether or not this is true or false. So my Boolean expression, my comparison is, if this dot volume is equal to that object volume, then these two health potions can be considered the same. And then we always end with a underscore case. This is the wild card. It's very similar to star in other languages. If it's any other type that is not explicitly mentioned here, and we could have multiple types here. We could have health potion. We could add dynamic object here, whatever else we want. If it's anything else, I want to return false. So that's my catch-all. If it's a type that I didn't explicitly mention how to compare it with another type and check if it's equal, just return false. I don't want health potions compared to any other type, so I'm just going to return false all the time. Now, this same exact code that we saw earlier has very different functionality, very different behavior. Printing out the potions gives us some more meaningful information about them. And comparing the potions is going to compare them by volume, not by reference. So both of these are going to be true since these two potions have the same volume of 4. Would you use make string over? I always use toString personally. So we're at the end. How many? I only got 2 more slides. I'll talk about them at least. So if you look through the jumper code in the handout for Physics Engine, if you look through the code that's given there outside of the Physics Engine package, the physics package, you'll see a bunch of game code. Most of it, it's fine if you don't understand it right now. We will use that as an example throughout next week as well. By the end of next week, by Friday next week, you'll be able to understand everything in the jumper, in that handout code. With the exception of the GUI, I should mention that. With the exception of that. But if you look in that code, we have jumper object, which is going to extend static object, which I only use to track and index a unique ID for each object in the game. And then I have the objects of the game, like platforms and walls, extend jumper object, and then override the functionality in dynamic object. So when you're looking at the dynamic object code in Physics Engine, it's just filled with testing code. It just tracks, was this method called, which face was collided with, etc. It's really useless stuff. It's only useful for testing your Physics Engine itself. Once we start building a game and adding game logic, this is where we override all that testing code. I'm going to override collide with dynamic object because I don't care about that testing code. I want to override that with the actual game logic code. In this case, I want to say when a dynamic object collides with a platform, if it collided with the top of the platform, zero out its z velocity, set its z location to the top of the platform, and then call its on ground method, because in this game we're going to consider landing on a platform the same as landing on the ground, even if it's not at zero, z equals 0 on that plane. So now I can get the actual functionality I need by extending static object and then overriding that default functionality, which is only used for testing. So this is why, if you look through that code, you're like, this Physics Engine doesn't actually do anything. What the hell? This is where it gets its functionality, is by extending those classes, static object and dynamic object. Our player class in Jumper extends dynamic object, and overriding that functionality with game-specific logic. And then we can use the same Physics Engine in any different game that has physics, because we built this generically, coding to dynamic objects and static objects instead of any specific stuff that's specific to any game. Same with walls. Walls extend jumper object, which extends static object. I'm going to override collide with dynamic object to say, if you hit me on the z-axis, don't allow clipping through this wall. In the game is the horizontal axis is z, and then the vertical axis is x. We don't use the y dimension in the jumper game. Which brings us back to the lecture question. All right, so that'll officially be the end of lecture, and let's do some chatting. We catch up on. I saw quite a bit of chat. Some of it was irrelevant, but I think I missed some good questions in there. Is that arrow function notation in Scala? Yeah, the Scala developers love their arrows. I'm not complaining. I like them too. But a lot of arrows in the syntax of this language. Right here. It's similar to a switch in C++, this match case, except it does do some type matching as well. So it's a little bit more than a switch. Or a switch is only checking the values. A match will also check types. Scala support the notion of case class. Case classes are like regular classes, which export their constructor parameters, which provide recursive decomposition mechanism via pattern matching. Did you cut and paste that off the internet? Yeah, case classes are they get some functionality built in. Case classes are used. We'll use these later in the semester when we get to Learning Objective 5. is if you give them constructor parameters, and that's it. You don't give any definition to the class, and then there's certain functionality that they get. One of the pieces of functionality we get from case classes is they'll always check for equality by their values. So if you have two objects of a type of a case class and check for their equality, what that'll do is check all their constructor parameters and make sure they're storing all the right values. It won't do comparisons by default. It won't do comparisons by reference. So that's one of the things we get from case classes. We use them for message passing across concurrently running code. There's a review session where there'll still be regular office hours at 4. Yeah, there'll still be office hours at 4 unless those office hours are from the TAs doing the review session. I didn't check the schedule, so I'll hedge my bets there a little bit. I haven't checked the schedule to see if that's their regular office hour time. Return Jesse. Yes. So, Spyman, that's actually what the demo I was going to do if I had enough time. Which I'll do during the chatting section. Why not? I would like to use the chatting to give more demos and really reinforce content. I mean, if y'all just want chatting, that's fine too. But I think that'll help you a bit. So here's the physics engine handout. And you can see where did I want to go? I want to start in game object. So we see game object. The functionality here, like collide with dynamic object that we override, doesn't do anything. It just has some bookkeeping code that just tracks if this method was called and what were the arguments that it was called with. This is useless. It's only useful for testing, and that's how you're going to test your physics engine code. But once we extend we extend this class in dynamic object, we pass along our constructor parameters, and we have some more just bookkeeping, just testing code. On ground just sets on ground called to true. Useless functionality, only used for testing. But when we go to our jumper code, our jumper object, again, just to track indices, I don't want to explain that right now. I did mention this a few lectures ago. I have an object and a class of the same type, and I'm using that to store a variable at the class level. So every time a new jumper object is created, I increment that index. So each jumper object is getting a new unique index, which I use as its ID. And then I'm going to extend jumper object. And here, platform extends jumper object, extends dynamic object, or extends static object, extends game object. And all the way back in the game object class, we had this collide with dynamic object. All the way down here in the inheritance tree, I'm finally overriding that and saying, I don't want that testing crap in here. I want code that actually does something related to my game. So whenever collide with dynamic object is called, we're going to take that dynamic object, check if it hit the top of the platform. If it collided with in any other way, an internal collision, a negative Z, face dot, bottom, negative Z, or positive Y. If it collided with any other face, I don't care. I want the player to be able to move through this platform. So if you're underneath a platform and you jump up, you should go through that platform. But when you fall down, you should land on top of it. That's the behavior I want. And that's why we compute which face was collided. So if somebody landed on the top of this platform, zero out their Z velocity and place them on top of the platform, and also call their onGround method, which is part of the dynamic object class, which doesn't do anything, but that's going to be overridden by the player to get some functionality out of that as well. So the player is a dynamic object in this game since it can move around, and there I'm going to override that functionality as well to make sure I get the functionality that I want. So this is how we can use this physics engine to actually get some nice behavior out of the game. So finally, back to your question. Should we see anything move? If I run this app, and wait for it to load up. I'm going to see the game and nothing happens. This takes WASD and also the arrow keys for the two players. Does nothing. Super boring. Lame game. Once you start implementing your, because of course it doesn't have any physics attached to it. So once you start implementing your physics engine, especially when you get to the primary objective and implementing update world, then we can start to see actual changes. So world stores all the static and dynamic objects for the whole game. So in today's lecture, we took this dynamic objects list and assigned it to a list with all the objects of our game that can move around. And we didn't have any static objects in today's lecture example. But we gave the world some dynamic objects. Physics engine takes a world in some delta time and updates all the objects in the world. So if I just wrote some really silly code here, this is not anything resembling a solution, just so you know. But if I say for dynamic object in world dot dynamic objects, dynamic object dot location dot z plus equals 0.1. So every update, and this is going to update, what do I have? Because I'm using GUIs. So this will update 60 times per second. So update world is going to be called 60 times per second with DT of 1/60th of a second. So we got a 60 FPS game running here. So every 60th of a second, let's update by 0.1. So we're going to move up at 6 units per second. So now if I run this, we should be able to see our change reflected here. And we see our players just kind of moving up. I still can't do anything. The buttons don't do anything. But something does happen. So as you implement your physics engine, you're going to add physics to this game. And eventually you should be able to play with WASD and the arrows, control both players, and be able to jump, land on platforms, and you shouldn't be able to move. These edges are actually walls. You shouldn't be able to go past the edges of the screen, the walls, because those static collisions are going to happen. And you're going to, if you have the right face being computed, you're going to only be able to land on platforms. You're going to be able to not move past the walls, etc. And of course we can, I recommend just playing around with this first. Do things like this. Like if I want to do 1.0, just get a feel for what you're actually building here. You're building the physics engine for this game. If I do 1.0, guess what? We're going 60 units per second now, straight up. And we can see the players just running through. Yeah, P again. I'm just not in the mood for risky clicks today. But if anybody wants to click on that, and it does show me a preview. Yeah, it looks legit. If that's helpful to anyone, go for it. You guys are all about these graphics cards and stuff. Oh, and we could, there's no point to. We could push that enough that we can break the game. If I did like 10 or so. Demo for today's lecture question would make people happy. I'm sure it would, especially if I went over the solution. Doesn't necessarily mean it's a good idea. But I can drop some hints. Right? What is can I drop a hint without giving this away? I don't know what I could say without really giving it away. I feel like this one's pretty straightforward if you are understanding Monday's lecture question. Even if you completed Monday's but you didn't quite understand it, then this will be tricky. Or if you didn't understand today's lecture at all, maybe. I'm not even sure what I would give to... If you have a specific question, maybe I'll take a shot. Yeah, you call the use method on each value of the list. Each of these methods, you should have a total of like 5 lines of code. Maybe... Probably 6 lines of code. Depends where you put your braces, maybe 7. But the code itself is pretty straightforward for this one. It's the testing. It's the testing where I'm really checking, do you understand this polymorphism inheritance stuff? The fact that you have to create a list of type electronic and store both boomboxes and flashlights in that single list of type electronic, which is what we did in today's lecture. We had a list of dynamic objects, and we stored 3 different types, objects of 3 different types in there. So I need you to do that same thing here, creating that list and then calling your code with it and checking each one. Did they, was boombox used with a draining charge of the battery by 3? Did flashlights drain the charge of the battery by 1? And each one of those, it's calling the use method from the electronic class. But electronic didn't define what use should do. Boombox and flashlight did. So even though these are stored in variables of type electronic, when we call the use method, the actual method that's called depends on whether that actual electronic is, in fact, a boombox or flashlight. So even though I said we lose a lot of functionality when we store like a flashlight in a variable of type electronic, you do lose functionality, but you can still get functionality indirectly. Call the use method, which electronic has to have, and then it calls that use method from the flashlight specific class, that flashlight specific use method. And then you can check, okay, that electronic was a flashlight, its charge should have been decremented by 1. That electronic was actually a boombox, its battery's charge should have been decremented by 3. How do we apply gravity to the vector? It's outlined in the homework, but you everything's linear. Don't use calculus. I've seen students go down that road before. Yeah, so it's velocity equals velocity plus gravity times time in the z direction, or minus rather. Somewhere you got to add that negative gravity, because the gravity is only the magnitude. Like if gravity is 15, you have to take 15 times time and subtract that from the z component of the velocity. But everything's linear. And the idea is our game is updating 60 times per second or 30 times per second. Once you're updating that much, your dt is small enough that we'll get close enough of approximation of calculus, of doing the derivatives and the integrals of all the calculus stuff. We're getting a close enough approximation with such a small dt that we can have linear updates and have it appear as though it's actually what it's supposed to be. The errors are going to be small enough that we're not going to care. So that's one of the big ideas of how we're updating things. Homework's due, the soft deadline is Sunday, whatever number that is. Do I have it different in different spots? I hope I don't. Oh, we're done with batteries and electronics. This is the last lecture question relating to those. There's a 3-parter. That's plenty. I don't think anybody wants more batteries in their lives after that.